To session 2 for the morning session with Jim Ladue. I'm meteorologist Dave Jones reporting live outside in a snowy Breckenridge, Colorado. 15 degrees outside right now, and it looks like we have about 2 inches of snow so far, and it's continuing to fall. Looks like some needles and flakes combined here. It looks like Jim is going to take over this afternoon or the next session here and go through some more live sessions with BUFKIT and getting some more of you online viewers up to speed on how you can use BUFKIT in snow like this, forecasting snow like this, and all that sort of stuff. So we hope you enjoy it. It's blowing out here. There are a lot of happy people walking around here in Breckenridge right now as the snow continues to fall. This is great up here in ski country, and so I'll throw it back to you inside as we learn more about BUFKIT. Take it away, Jim.
Okay, I just wanted to show you something. It's on the screen. While Dave was outside in the snow, I took a picture of my sleeve. And this is going to fall straight into our next session here, and we're going to be talking about snowfall forecasting, and specifically snow ratio forecasting. And yeah, I scraped my head pretty good, so I know this stuff is real. Thanks for the sanity check, though. Anyway, so I'm going to show you a sounding. This is actually taken from right now. This is actually Boulder, Colorado. This morning's ensemble forecast. Actually, this is the NAM forecast here. Actually, the ensemble too. But you see, we have, again, it's very steep lapse rates. This is not a three-layer kind of thing you get with a warm advection kind of precipitation system, but this is definitely cold advection and very strong cooling with time. You can see if I back up a little bit, starting off, watch this sounding just peel off to the left towards the colder part of this QT. Now, if I go to about this time, actually it's a little bit before that, but here we go. And you can see that it's cold out there, and we got the dendrite, the snow growth region is way down low. You know, it's way down this region right here. Not too much. The model from Boulder doesn't have that much vertical motion. And you can see it's a little bit shallow. In fact, you know what? I'm going to go ahead and expand this out a little bit here so you can see a little bit more clearly. How's that look right there? Oops. Just adjusting this so you get the maximum resolution right there. So I don't think there's any question that there's like a precipitation type issue. We don't have to worry about this display right here. Instead, we're going to talk about something else that's on the overview. And let me zoom in onto the 24-hour. And we're going to go to precip accumulation. Well, one thing here is you can see the high RHs. And here we are firmly embedded in high RHs. If I look at the snow growth zone, it should show you very low to the ground. It's right there, literally right next to the ground. In fact, it's so close. If I actually adjusted... if I could, yeah, I would actually adjust that, and you'd actually see us probably sitting at the bottom of the snow growth zone. I mean, it's that close, at least at this point right here. Let's see, if I went to feet, you see that? I'm changing my vertical scale, feet, kilometers, pressure. If I go to feet, there we go. There we go. Okay, so we're probably about a few thousand feet above Boulder. So we're sitting right about here, right in this zone right there. So that's impressive. So if we did expect all this lifting, let's say forced topographic lifting over the mountains, we would expect to see dendrites, or mostly dendrites. I don't know, what do you think? There's needles in there too. There's quite a few, and there's very small flakes. In fact, my iPhone was not good enough to get, I need an iPhone microscope, to really zoom in on that. There's an app. You can get an attachment, like a lens attachment, which you can put on. It's like a macro lens, and it'd be awesome. You could actually go and take a picture of your sleeve, like individual flakes, crystals. It'd be great. So, so we don't have a great picture, but I think we saw a few dendrites and needles. Needle formation is often favored a little bit warmer than the dendrite production zone. You probably see it at the bottom, literally right here. So I think the temperature outside was about 15 Fahrenheit. Let's see, what's that in Celsius? It's about -8. Is that right? -8 to -10? Yeah, almost -10. So it may, some of the snow may be even being produced like literally directly above the hotel. I mean, that close to the ground in some cases. Some of the other flakes are probably being generated higher up, up in the in that snow growth dendrite production zone where it's a little bit colder. But we're going to talk a little bit more about that using a canned case.
Can I just ask a quick question here? Because a lot of what you've shown so far has been like specific point forecast times. Can you take it and kind of move it along? Because the way I'm using it, I kind of advance it through the time and watch how things evolve and the sounding and things like that.
So the question is should we be looking at the evolution through time?
Right.
Yeah, and that's the advantage of the overview is you are seeing that evolution through time. You're looking at what the trend is and so forth. Right. And if a system is moving, with good behavior, then you can convert that to time to space. But yeah, so you can see right here as we're going through, you can see the drop in that dendrite production zone. And over time, as we get too much later than this, the forecast is for considerable drying down at low layers. So we may see the snow tail off in the form of larger dendrites, if I'm right. I could be wrong, but I'm going to kind of guess that it's going to go towards that direction. Let's see. I have another question in the back. Yes.
Can you show us again in BUFKIT where we would be able to see the difference between dendrites and needle growth? I kind of missed that.
Oh, that's, yeah, I know. The question being dendrites and needle, and where is that, and how do you know? And maybe I'm just talking through my hat, but I didn't get through the next case I was going to go through was a snow ratio case, and there's a diagram, and I might have to kind of search for it here. So if you bear with me, let's see if it's on this page here. If it's not in this one, it might be in the next one. No, it's not in this one here. So after all, I am
Thinking this is great for powder forecast for skiing.
yes. There's actually, I don't know if you know of, there's a professor out of University of Utah, Jim Steenberg, who wrote a paper forecasting specific snow ratios for Alta. And he came up with, in fact, all ski areas in Little Cottonwood River Basin. And he came up with a scheme that really makes sense, which is basically looking at the wind speed and the temperature at mountaintop level and so forth, and then saying, based on an algorithm he produced, it's like, this is what the snow ratio forecast is going to be for this Little Cottonwood River Canyon and everything in between. But it's so specific out here with the topography that, from one place to another, it's going to vary quite a bit. And the same is true for lake effect. If you're close to the lake with an excess of liquid water content, your snow ratios are going to be a lot lower than they are once you've extinguished a lot of that liquid water content, and now you're not rhyming so much, but now you're just creating snow through deposition. It's just straight from water vapor to ice crystals. And so we see that a lot. I was up in Lake Ontario once back in '94 in January. We measured a let's see, what was it? It was like a 14 to 17 to 1 ratio right on the lakeshore. And it was all grapple. And it was 0 degrees Fahrenheit at the surface. And a convective layer. It was like 3 kilometers deep. It was a huge lake effect event and extremely cold. Yet we still got grapple. Once we went inland, that ratio went up to 30 to 40 to 1. And so did the snow depth. It's like... So... Sure, some people don't call that real snow because it's so fluffy. It's like the snow snobs in the Sierra, say, our snow is real concrete. We got good 8 to 1 ratio. You love that kind of stuff. And it's like, but you ever try skiing through that? Yeah, that's right. Okay. I might have it on the other PowerPoint. Let's see. I'm going totally off the script right now, so you guys are getting the benefit of that. Oh, I thought I had that on there, but this is all different kind of events. So I must be hallucinating. I thought I had that diagram up here. And if not, desperation will ensue, and I might have to go off to a different PowerPoint. So bear with me, and I'll get that diagram up here in just a second. I'm going to Ed's PowerPoint from last year because he had it in there. Okay, if you see it in the slides there, let me know and I'll stop. There we go. Does this diagram ring a bell with you? Okay, so this is a diagram which shows needles from -5 to -10. But you notice that it depends on the supersaturation. So if you have like a gargantuan amount of vertical motion, you actually may transition to, you may have higher supersaturation because you just cannot convert the liquid to ice fast enough. And so you start ramming up against that. And so you may see, more needles. But it's really hard to tell, especially with the flakes this small, whether we're in this phase or this phase. But I think we have a few, we're certainly not in this regime, 0 to -5, so we can rule that out. I think we're closer to over here. And then as we get over here, now we're starting to talk about dendrites. And the stronger the, good, decent vertical motion, we get more classic dendrites. Now, a lot of this stuff, presupposes that you don't have any rhyming. And so if you actually have direct contact with liquid water clouds, you're going to get that rhyming, and it's going to muck up the purity of the snow crystals. And that's where, most snow falls in that regime. You'll always have little frozen cloud liquid water droplets, attached onto, the crystals that were deposited by pure direct transfer from water vapor. And so that's why to get nice pure dendrites is so rare. I mean, when you see something like that, consider yourself lucky, especially if you live in Atlanta or Norman, something like that. Which, coming to think about it, I do have a case from Norman. Let's see if I can get that back up again. There we go. Oh, let me just skip over that one right there. This one. Okay. So we'll go to Norman here, and this one is a good one because we have a bunch of weather weenies in Norman, and they're constantly measuring snow and melting it and getting liquid water equivalent, and then we're arguing on Facebook or Twitter and about who's right and who's wrong and so forth. So it's pretty good. And I think Paul might have shown this case. Don, do you remember if Paul showed this one or not? Maybe he didn't actually show this one. Okay, well.
I think he showed the earlier one, the first of it.
Right, okay. Yeah, that was the Groundhog Day blizzard. This is the setup that produces the highest 24-hour total in Oklahoma. So it was last year, and here you have the trough rounding into the base of the mean trough, the shortwave trough. And as we go on, you can see, look at these temperatures are super cold. I mean, it was -40, it was probably -40 degrees around here in Breckenridge at the time. It was certainly that in Crested Butte. So it's the coldest air of the season, basically out here in these longitudes. And down here at 850 millibars, you can see that surging Arctic front barreling down through the Texas Panhandle. The trough coming in from the west, and we have a Gulf feed coming up from the south. We have a pretty good setup for a winter storm in the southern plains. So see at 925 millibars, Norman is on the cold side of it, including most of northern Oklahoma. And it's pretty much below freezing all the way up the column around here. So, to have the Norman not have a question of rain or snow or freezing rain is a rare thing. So you look at this. This is an amazing. Look at the temperature here. It's 81 degrees just down here in Pedro, just south of Wink. Is that right? Is that Pedro? I think that's Pedro. 81 degrees, while it's 9 degrees in Lubbock. Tucumcari carries 10. So the 70-degree contrast. And then it goes to 3, then to -2. Garden City, -2, gust of 30, quarter mile S plus. I'm sorry, plus SN. Yeah, that's when they go to fog and then eventually like meteors or something else. It's just, It's ridiculous ASOS in these schemes, but they're actually getting away with it here. Yeah, I mean, it's that's just nasty. But I'll tell you one thing, the feedlots were probably still liquid water. I was up there in one blizzard back in '97, the one that closed the new Denver airport. And, yep, it was a blizzard in Garden City except for the feedlots. It was rain there. So anyway, off that subject, here's the frontogenesis from the SPC meso plot from this day. They ran out of contours somewhere around Lubbock. So they need to reset this. That is the strongest signature I've ever seen in this plot. And so what did that yield? Well, there's the snow band right here, setting up right in this region. And the front, of course, is phasing in. This is the potential vorticity anomaly coming in from the west. And you see the phasing is going on right there, which is obviously going to yield a very deep vertical motion pattern going all the way up. And so, yeah, the evening we started out rather benign. Our sounding is below freezing, but with a shallow moist layer, but nice warm advection signature. You can see in that wind profile veering around from northeast to southwest and then to west. And so we'll take a look at some ensemble wharf soundings. This one here is an 11-hour ensemble wharf sounding that we produced. And you can see that this is, what's this valid for? I guess just about an 11Z, of course. It's a 0Z run. So at this point here, I'm going to go ahead and break into, I knew since I went off script, now I'm going to have to find these profiles. So let's go ahead and get back here. Somebody's going to have to help me with my memory. Was that case number 5? No. Case 4. Okay, so yep, that's the one. So I'll take that, and we'll copy those files straight over into BUFKIT. And we'll put this in. So now I'll just go over to BUFKIT, and at this point here, I'll click on Ensemble Wharf. Now the great thing is, when you get to the ensemble models, whatever distribution site there is, they usually come in a zipped up file format. So you actually, when you suck those in and put them in, the BUFKIT puts them in the BUFKIT data directory, you just click on one of these models and it automatically unzips them for you. And then, so it's pretty much painless right there. So let's go ahead. You got Ensemble Wharf. Okay, so I'll pick the Norman sounding right here, and oh gosh, let me get that back into this space. Oops. Okay. So we have from 0Z, we'll advance forward, and you'll see the column cool down low and stay about the same temperature aloft. So we have the Arctic air infusing in. And at this point here, I'm going to go ahead and point out a couple things. Snow ratio. This is what we're going to concentrate on. At this point, it's not a question that we're getting precip forecast. Starting around 4 in the morning, and then you see the model omegas. They're pretty strong up aloft here. Most runs have it, the same general picture. The model omegas, how do the model omegas relate to the snow growth region? Any comments? Above, below, right on it?
A little below it, aren't they?
A little bit below. Does everybody concur? Okay. Let's see. How about later on? Look at the snow growth region. Watch this. Now everything's a snow growth region, and it's all pretty much saturated too. How about here? What do you think about this time? Is it closer as the model omega? I know there's a lot of spread here, but let's turn off the ensemble and just focus on the main run here. Okay, how about now? Is it right on the omega, the snow growth region? You have no choice but to say yes. So please say yes. Okay, thank you. Okay, well, let's take a look at the overview now, and we'll go to 24-hour. Come on. There we go. Okay, you notice a couple things. I have my height coordinates highlighted here. I'm going to go ahead and click on this checkbox to highlight my precipitation accumulation. Now I got precipitation accumulation up here. Precip checked out, accumulation checked out, Bourgeois, it doesn't matter. Turn on and off that. We're going to concentrate on this area here, which is this snow forecasting part. So I'll click on that, and we just converted the liquid equivalent to hourly snowfall right there. And when I go to snow accumulation, it goes right off the top. Well, that's out of control. So I right-click on the labels over here, basically the coordinate relating to snowfall accumulation, and get that down to somewhere in control. And here, I want to show you this. I'm going to click on the ensemble. So this run is rather modest. So we'll keep it. I tend to rather be pleasantly surprised, and that's hard to do in Norman when there's winter storms concerned. Okay, we got RH, and look at this. Okay, modest accumulations, and then bam, right around 11:10Z, we get this burst, this several-hour burst. And I think that's when that frontal band started to come in. What happened is up north, the frontal band, the front end of that band was more in the warm convection zone ahead of the main. Well, I don't know if it's not a surface low, but somewhat elevated, so it was stationary. And the southwest end of that came sweeping through like a cold front. And when it came through, it was just like, you can imagine a winter equivalent of a squall line coming through. And it was just like that. So the models were forecasting that. So anyway, let me turn off the RH. You can see this is the deep ascent with the high RH, and I'm going to just turn that off. Concentrate on the relative location of the omega to that of the snow growth, okay? That factors into snow ratio forecasting for one scheme, one kind of scheme. There are other schemes available. Max temp and profile happens to be the one displayed right now. Max temp and profile is where I have, it takes the maximum temperature. So if I was here and I look at the profile, it would take this and it would use a lookup table with some pre-established snow ratio for that particular max temperature, which is around -8, something like that. Okay, so anyway, let's go ahead back to the overview. So max temp and profile, there's one thing I want to click on. This is snow ratio. Let's see what the snow ratio is forecast to be. Okay, now this is using the left vertical axis right here in the labels. The blue line is the snow ratio. You see it's 20-to-1 or better. That's crazy. That's max temp in profile. Okay. And it's honestly, it's understandable. It's a simple lookup table, and it's a very low maximum temperature. It corresponds to a very high ratio. Maybe we could use climatology. How about that? It's set on 12-to-1. I can adjust this. And you can adjust it actually to fit your climatology. But how do you know what your climatology is? Does anybody know what your climatology is? Nobody knows which. Of course, for some people there isn't a climatology, but
Miami is 0.
yeah. yours.
Eastern part of my viewing area, it's around, I think, 11 to 12 to 1. Western part around 13 to 1.
11 to 1. Okay. Would you like me to verify that for you?
Go for it.
Okay. Oklahoma City is. Oh, I keep forgetting. Here we go. This is a study based on Marty Baxter. I think, did Ed go through this last year? No. Okay. It's a study by Marty Baxter. Which he took data when there used to be reliable data before METARs and ASOS at that time. Actually, it's getting reliable again, but it's totally different observing networks. Oops, let me trying to scale this so you see the color bar. Okay. Okay, how does that fit for you? Is that, yeah, that's pretty close. Whoa. Okay, see the overlays coming up? Okay, so for Cleveland, you see that we have 14.5. Lake effect zone influences this. And you see that the distribution is right-tailed. So there's some lake effect events that must have really high snow ratios in Cleveland. Around here, it's tough to say. I mean, you know, these contours are based on surface observing stations. But when you have the diversity of terrain out here, you can sure as hell bet that it's a lot of variation, very close. So this one here, 15.2, 18 to 10. I mean, that's the ratio. There was a storm last December, I think, where it was probably in the bottom, but we'll see, pretty high. So in Norman, 11.6 is the average. And so it can vary up and down the scale right there, as you can see. Okay, so let's go back and let's look at the overview again. So I'm going to go 12 to 1. That's pretty much climatology. And see now what you have for ensemble prediction is considerably more conservative. So is that right? I'm not sure. We'll find out. And that's with a 12 to 1 ratio. So, you know, not even considering what the QPF is or what those errors are. So we're compounding uncertainty with uncertainty. You know, we have an uncertainty in the QPF, and now we have an uncertainty as to what ratio we're going to forecast. Let's go to this one here. Now we're going to look at a ratio. This is a scheme that started out with actually a PhD dissertation from McGill University in Montreal. And then it was converted to an operational use by Dan Cobb, who was the Sioux in Caribou when he did his work. And he teamed up with Jeff Wallstreicher in Eastern Region. And what they do is they look at the maximum vertical velocity and where it falls relative to the dendrite production zone, or that snow growth zone. So if you have a large fraction of that total profile in vertical motion falling in that zone, you would expect a large fraction of dendrites to come out of that, you know, assuming you don't have any icing or anything like that. So with this one here, we have, let's see, the profile of omega. You can see it gets fat down here, narrow a little bit up here. And so what happens is initially you can see the ratio starts fairly small, even less than 10 to 1, as most of the omega is down here at this time. And then as the omega lifts up into the dendrite production zone, you see the snow ratio start to rise up too. And it really jumps. I mean, it's out of control. And then look what happened later on. Now you can see what happened is the dendrite production zone basically falls to the ground. It gets so cold that it's minus 15 or so Celsius all the way down to surface. So if there's any saturated ascent going on in here, it's going to produce quite likely dendrites. And now look at the snow ratio goes through the roof. So what is the storm total ratio out of this thing? Okay, well, here's a handy thing. I can start on the right side of this overview, holding the right mouse button down, and I zoom to the left side to the end of the storm, and I get a storm total of 4.2 inches. I'll talk about the other number in the parentheses in a little bit. But okay, so that's 4.2 inches. Now, this is a little bit clunky, and we probably need to do something about this, but oops, I want to keep that right there, and let's turn off all the snow. Let's see what happens. I'm going to get the liquid equivalent. 0.37. All right, so does that sound fairly reasonable? 4.2. Can somebody divide for me 4.2 by 0.37? You have an app for that. That's great. Well, it's close to it's probably close to 10 to 1, right? Because it's 0.4 to 4 inches, so that's that one there. If I went with max temp and profile, okay, same QPF. Now let's add all this. And now I get 6.5 inches. Okay, if I go with climatology, I get 3.5 inches or 3.6 or whatever. Right there. Okay, so somebody was going to ask about what's that number in the parentheses. You notice there's two profiles here, this one and this one, the white and this purple. The white one represents compaction included. So for every hour, there's an exponential compaction factor that's included in that, so that you see immediately already it diverts away from the no compaction accumulation profile here. So this compaction profile is supposed to add some reality to this, to what we really see, and that is snow is always compacting as it's accumulating on the ground.
So when you
Yes.
train forecasters, then do you train them to go with the compaction total for accumulations in their forecasts, or snowfall accumulations in their forecasts?
We will go with the compaction. So the snowfall. And you see, this is the one thing, because here is, like, truth is dependent on the observation. So it's kind of like the Heisenberg uncertainty principle, the person observing it, whatever that ground truth is just as important as the forecast. So you could forecast to somebody doing hourly snowfall, or you could forecast to somebody that's measuring at the end of the storm. And so what's the important snowfall that you guys forecast? Is it the hourlies, 6 hourlies, or storm total? Okay, mostly storm total. Yeah, and so do I. One thing is there is an important factor to the hourlies. If you have excessive hourly snowfall, that's extremely critical to clearing operations and airports and things like that. So,
I think it depends on how long
yeah,
duration it is too.
right.
Schrodinger's cat aside, what are the variables on compaction?
What are the variables on compaction? Okay, well, that's a good question. You're trying to stump me, I think. Okay, variables on compaction. This compaction only assumes that there's no melting, no drifting, that it's just purely snow accumulating on the ground over time. Once you get to those other variables like drifting and melting, then you're talking about other things that are not included in BUFKIT and that you have to factor in. And if I have time, I want to go to some convective cases, but I have a case here that highlights that, and I could probably show it a little bit. Maybe some of you recall. What is that?
Temperature is not really a factor.
Temperature, we're assuming that everything's safely below freezing. The entire snowpack is below freezing. Ground temperature starting out below freezing. So that we're not seeing the heat transfer coming up and eroding the snowpack from beneath.
Use the microphone, guys, please, when you talk.
Oh, I'm not paraphrasing. Yeah, I'm sorry about that. Okay, so here's the thing is those factors are not included. So how many of you remember the snowburst in D.C. last year, end of January? Were you stuck in the, Dave, were you stuck in that, or?
Oh, no, I saw it coming.
Okay, you saw it coming. That's good. Yeah. You see, a lot of people were stuck in that, and because they had this kind of deer in headlights effect, which is...
The snow melted. It melted on the... Hey, Dave, you want to use the microphone?
Somebody asked Dave to use the microphone. Very good.
No, I was just going to say the snow melted and the rain washed all the treatment on the roads off, and then it quickly changed to snow
Yes.
at a rate of about 3 inches an hour. So
And that was a convective snowburst. And the problem is, of course, you wound up with a ground that was warmer, and then you got all this snow on top. It melted. And then if you just took a straight ratio, it just made no sense whatsoever. And it's completely unrealistic. But by the time you get up to New York City, they started out a lot colder, same convective snowburst, and so a lot more of it stayed on the ground. They got a storm total of 19 inches in Central Park. So it was, and that one was a tough forecast for the forecast office too. I mean, they got it right. They really hit the headlines pretty hard, but I think the sanitation department was only expecting a foot or something like that. Foot, 19 inches.
And I think their biggest problem there was rapid rate of snowfall, and cars got stuck on the road. That was the day before Christmas.
That's right.
And I think that was the problem.
Oh, that was a different storm. That was there were some issues with that one, which I won't go into at least at this point because they were non-meteorological. But with this, at least the DC one, a lot of people were just caught off guard. They waited until they saw the heavy snow fall, and then they left. And now, as a result of that, the Office of Personnel Management has updated their guidelines, and they're now going, if you see that kind of thing happen again, we're going to hold everybody over and stay there. So we'll see how that flies. Okay, so we go back to this case here, and I think we've seen all the scenarios play out. So I'm going to go to what I measured, which was 0.31 inches. So it's fairly close to that one ensemble member that we pointed at. Okay, the depth of the snow, I should go to slide view format, but the depth of the snow is basically, let's get to that work page here. Well, actually, I should probably measure that, but, let's see. The total depth was like 3.7 or something like that. Well, I could probably type all this stuff out here, but, that's probably close to 10.1 and so forth. As we go through this, the max temperature profile was by far the most aggressive in terms of ratios. So, actually, I think I'll just talk through this and not fill out this table here. I'd like to make you guys fill it out. It'd be kind of hard to do that. So here's another thing we're looking at. You saw the big spread. If I picked another ensemble member, it was more aggressive and so forth. But the max temp and profile is pretty much uniform across the board. Not the Cobb or the snow omega technique. The model is extremely volatile with its profiles of omega. It depends on whether the sounding fell into a frontal band or outside of a frontal band. It's going to get even worse with higher resolution. In higher resolution, the model could wind up in a thunderstorm updraft, or it could wind up in an outflow boundary or an edge of an outflow boundary. We already have problems with lake effect. Your model could wind up in a lake effect band and yield completely different results than if it was outside of it. So some real questions are going to come up as to what is considered a near storm or representative sounding in this case. And this is an example of what you're going to see, this huge amount of spread between this technique because of the varying volatile profiles of vertical motion. So be warned on that one. It's going to be messy. There's a new Cobb technique. Some people complained about the snow ratios being too high, that it was coming out with snowfall forecasts that were too aggressive. So they made an update to the study and came up with a modified, toned down, less aggressive technique, which is the Cobb 11. Depending on which one is correct, we'll find out at least here coming up. So let's go ahead. Post-mortem. Okay, so the snow started down here. First of all, there was one ensemble run that was forecasting 18 inches for us, and I was really excited. And so was everybody else in the test bed. That was the day where the test bed during the briefing filled up to like 80 people. And everybody was just like salivating over the prospects of this one NAM run, 15 to 18 inches. Well, here's reality. 3.7 inches, at least at my house, and this is out just east of Norman. And the lower part of this was a 6-to-1 ratio, measured in several places. Other people measured similar ratios. And then the upper part, I took this last part up here and measured a 16-to-1 ratio. And all of this up here is pure dendrites, some needle clusters and things like that. A couple rind plates, but otherwise, actually, you know what? Now you have to fix that. I'm not going to let that one get away. Okay. Sometimes people make errors in here. So this is all pure dendrites. This actually won't let me type. Okay, well, you get the idea, right? This was all pure dendrites. Thank you very much. Okay, and this is all rind plates, needles, clusters right down in this area. Let me show you another picture. Okay. Oops. Now this one. I don't have that other picture. Okay. These dendrites, by the way, were some of the most beautiful dendrites I've ever seen. They're absolutely large, you know, probably about that big, almost as wide as my finger was. And it fell. I think we saw this scheme where we had fairly low ratios, and then right at the end, these super high ratios forecast as the moisture profile got shallow, but the dendrite production zone widened out down below. And I think that's why we started getting that last bit of the snowstorm was just that pure fluff and high ratio stuff. So we started out early with an out of phase omega profile. The omega profile was forecast to be roughly below the max dendrite zone. And then later on, we had this shallow cloud layer, but super cold. So that cloud layer was in the dendrite production zone. And here's the picture. Look at that stuff. You know, so it's just, absolutely gorgeous. And it was just because of this area right here. It's just coming out of this. No excess rhyming from excess moisture because this is the tail end of the system. It's just like the last bit of moisture available. So anyway, that case, at least this point. So,
Jim, I've got a question.
Yes, go ahead, Don.
You mentioned the very heavy values we had further north and east.
Oh, yeah.
Did okay. I have a question. The very large snowfalls north and east of Central Oklahoma. What about the ratios up there? Were they similar to what we had, or was it?
They were much higher. They were much higher in that main band, that main frontal band. They were like 12 to 14, 15 to 1. I think it was Veneta that had the 26 inches, I believe, or
In 24 hours.
that's right. And Veneta, that was just pure fluff up there. I think it was just, yeah, that was where the frontal band maxed out. I think if I go to, yikes, here's Ponca City. So Ponca City was in that frontal band. And look at these, look at the Cobb technique does. It's maxing out 25 to 1. It's all over the place. If I pick ensemble, yikes. Well, you can see the ensemble, there's a lot of volatility there. I'll turn that off. There's one. Pretty good ratios and so forth. That one's a little bit lower. You see the omega is above the dendrite production zone.
In this type of situation, is it reasonable to use the ensemble spread as maybe a forecast of snowfall range?
Okay, yeah, so the question is should I use the ensemble spread as a forecast of snowfall range? And yes, I would agree so. But you know what? There's a catch on that. If you're in warning mode, and this is actually maybe an opinion of mine, so it's kind of a soapbox, but you may want to exercise or, let's say, attention to people of the possibilities. So if it's a reasonable possibility, and that would be up to you to decide whether, hey, this, yeah, most of the forecasts are, for 6 inches, but, we have like a significant minority of members. Obviously, you're not going to tell the public about ensemble members, but, there's a reasonable chance that there's a high end. And it could be, the forecast could be bimodal. It could be something where you have this cluster that's gravitating towards this big event. And it could be because it just happens to be forecasting the frontal band to be situated right on top of you as opposed to displaced somewhere else. And that's the problem with point soundings, is that you're not seeing it in context with, well, maybe the model is forecasting a huge frontal band just off that sounding and you're not seeing it. Yeah, go ahead.
If your omega is above your dendrite production zone there, what typically happens?
if we go back to the other one, I think we go to plates, cylinders. So you're getting snow. Yeah, it's just that you might not get the fluff factor because you don't have so many facets in the individual crystals that can latch on and leave a lot of air in between. So you want to have a lot of that, but there's another range, that warm range, where you can get dendrites too, -5, -3, where you can often get that fluff factor. And that happens actually a lot in the Sierra Nevada. You can get fairly warm uplift, fairly shallow, and yet huge snowfall rates. Okay, let's see, where were we? I'm going to depart winter. Yeah, I know, it's almost over with. Yes. Well, according to the model forecast, it was going to continue on for another couple hours, I guess. And
satellite has another enhancement north central Colorado.
that'd be good.
Might get another piece of that.
Okay, so we have at least some take-home points in terms of that. The one thing I did not show, and I should show, and I'll just show one picture. This is the forecast for that DC event, the snowburst. And we have a little option here in the overview called Elevated Cape. And this is a good transition to the warm season. And I don't know if any of you have used this or not, but what does this mean? Elevated Cape means that anywhere inside this, if you launch a parcel, you'll have cape, you'll have positive buoyancy, and you'll get convection. So you can launch a parcel way up here, and there's a possibility of convection. You can launch it down here, same kind of thing. Thunder snow. It's a great thunder snow forecasting tool. And so the models were forecasting this snowburst, and with the elevated cape turned on, you could probably see that it was quite likely it was going to be convective, and therefore, possibility of lightning. Now, could you get lightning out of non-convective, really strong lifting? Yeah, it's going to be hard. Roughly, you need about 5 meters per second of total ascent to get charge separation. If you don't have that, it's going to be tough to get enough to get lightning. Okay. Okay, let's see. I don't know if there's anything else here. So let's go over to the next PowerPoint. No, not that one there. Any other questions before we go on, or you okay? Okay. Okay. I have a series of cases here, and I'll leave it to you if you want to pull any of these down, see what comes first. And this is before we have to leave half an hour or maybe 30 minutes, 20 minutes, 30 minutes, whatever time you want for a lake effect session. 45. It's 11:06. Okay, we don't have much time here.
Well, before you get into that, then can I ask a question?
Yeah.
So, for all the streamers listening in South Florida, I'd like to know. You have the ability, yes, to move your ensembles or your sites around, your sounding sites around, your forecast sounding sites around. Has there been any thought to moving them into like a hurricane region offshore, because it's model based, it's actually site based, right?
There are, depending on what site you have, there's buoy sites. So buffer, NCEP, the National Center, produces buffer soundings for numerous buoy sites offshore, and others too, just random lat long points that seem kind of strategic. So yes, there are those available. And I think they're available on Penn State, probably some local offices, and also I think we're doing it at ours too.
I was just wondering, like, from a latitude, longitude point of view, because then maybe you would see how the GFS is handling dry air entrainment into the cyclone and stuff like that.
Right.
Well,
that would be a good question, whether, assuming the model is right,
Right.
then yeah, you could probably inspect it. But In some cases, though, since the sites are much further apart out there, it might be hard to really nail what you want, and you might have to go to a grid-based kind of thing.
Right.
Yep.
Okay, thanks. Back to winter.
No more winter for the next 20 minutes. It's going to be something else. We have fog, high winds, heavy rain case, severe storms. Oh, this is trouble. All right, how many want severe? Okay, how many want high winds? I'm afraid the severe has it. I'm not complaining, though.
Don't be afraid.
Actually, my personal favorite would be fog, but yeah, it was a really good fog case.
I'd like to vote for fog and momentum transfer if we get a chance to talk about that.
Momentum transfer. It's a good topic. There were a lot of cases this year from that. Let me go ahead and download a few more cases here. Okay. You got a BUFKIT cases. I have to remember which one it is. Okay, 7. I'll do 7. And do these 3. Now, I might move along a little bit faster to go through this, so we'll just see what happens. So that's 7 right there. That's high wind. Okay. And so do that. Okay, I knew I should have just grouped them all together, but the problem is if you do that, some of the soundings actually clobber each other. So you have to be careful about that. Okay. Let's see what we got. Let's do case 10. That's not an obvious one. It's difficult. Well, maybe it won't be for you. Let's see what happens. Okay. Now we'll go ahead and go to that one. See, we need 8 hours. We actually need 8 hours. Okay, here we go. Back to Norman. You're going to get a sense that I'm a little bit Oklacentric here. So we have, this is mid-June, and we have a wave coming in from the west. So the wave is rolling out. Typical latitude, actually, we're actually going to get some shear, and we have a low-level jet down below coming up. So pretty good. Even at 700 millibars, you're getting 30 knots at Amarillo. That's pretty good for this time of year. So we have a sounding. This is the morning sounding. So if we modified that, what do you think the afternoon temperature would be if we removed all the inversions? Ridiculous. Okay, so it's a cool summer day. So we skip to the afternoon. This is a funny day. We had all sorts of mid-level convection. It was just everywhere. You know, Virga, Mammatus, but nothing with actually a cloud base that we could recognize as something. So it was really tough to figure out, okay, which is going to be the big storm, because we were expecting some pretty decent storms on this cold front, you know, right here. And finally, one came up and had a really circular anvil with sharp edges just west of town. We thought, that's it. There's the surface-based storm. So, actually, I can go to BUFKIT here, and let's see, let's make sure. Let me pull that up. Let's give it the ruck. Oh, I didn't get the ruck there. Yep, that's still February. Hang on.
This is where I just closed the program.
I think I'm just going to do the same thing.
Just like forget it.
Yep. This is where I go, oh my gosh, how embarrassing. Make sure I get that right one in there. Okay, case 10. Yeah, those are, no wait, that's case 10. Yeah, that was EWRF, okay. Standing by, standing by. EWRF and Ruck. Oh, this is Windows 7. Okay. Hopefully that didn't clobber everything, but let's see what happens. That's June 14th. Let's look at the Ruck model. And you notice how I'm set up my scale for winter weather? So I got to really bring down, kind of zoom out a little bit here. Okay, so there we are. Okay, for this one here, let's go for a decent afternoon. Actually, this is the late afternoon. This is, okay. Okay, somewhere around there, 4 p.m. And we'll start off with indices. So indices are rather interesting. We have Cape Sin, so we have like 1900 joules per kilogram of Cape. It seems to be a lot of Sin there, which seems interesting. A lot of decent helicity, but not great, so it's green, not red. Okay, Cape is red. EHI, it says 1.3. It's above 1, so it's painted as red. You know, so that's rather interesting. I'm not going to go through all of these here, but notice down here is LCL. It's so high it's not even colored. So it's basically nothing right there. PW. And let me go ahead and draw elevated Cape. Let's turn on Cape. Let's turn on LCL, LFC. You notice the labels coming up? Okay. Yeah, I could use convective condensation level, but I don't think so. Convective temperature, it's off the charts. And wet bulb 0 and equilibrium level. I like equilibrium level. So we'll do that. And now you can see what the profile looks like. Now let's take a look at this. This is Cape shear. Okay, and you notice that we have current dot and then one previous hour. And so on the bottom we have 6 kilometer bulk shear. Well, that's really just the wind difference between the surface layer and 6 kilometer layer. Somewhere thin layer around 6 kilometers. And then we have Cape, which we can change from right now that's surface-based Cape. We could also change it to most unstable Cape. And you get that, but I think the same picture results here. But if you had elevated convection, you'd want to use most unstable Cape, right? That's the MU Cape. So anyway, based on that and that storm coming up, and this is near the time and a pretty good near storm environment, what do you expect? What kind of storms? Ordinary cells, supercells? And for those of you that don't know the answer, please do not raise your hand. Don. Okay, so what do you think? Is there enough Cape for a thunderstorm? Okay, so we got that. So it's not a question of Cape. Is it is there enough shear for a supercell, or do you want to stick with ordinary cells? You say ordinary? Okay, so a raise of hands. How many say ordinary? And how many say supercells? And how many of you say, when I see a radar picture, I'm not going to know what to call it? There are cases like that. Okay, so I'll take a look. You want to see a photograph, by the way?
Yeah. Now you change my
You know, you just can't look at assessing this without looking at a photograph. So we can zoom in if you want. And that's what you have, or zoom out like that. It already pastes for you the left and right movers. This is based on what we call the, well, it has several names. The internal dynamics method is one of them. Bunker's method How many of you have heard of that, Bunker's method? Okay, so it's, yep, this would take the rest of the session to walk through this, but essentially the Bunker's method takes the mean steering layer flow, and then the motion is to the right of what the shear vector would be in that deep layer. So it's right of the shear vector. My shear is pointing this way. It's going to be to the right, to my right side, and the left mover will be to the left. And the Bunker's method usually goes about 8 meters per second, 16 knots or so to the right and left of my shear vector. But with a storm motion, the steering layer flow is the starting point. It does that. It's a pretty decent, it's the best method out there. And of course, it's not perfect or anything like that. There's lots of gotchas and Quidro pros, but fewer of them than the other methods that we have. So it's got a storm motion, if it's a supercell, straight to the east. If it's an ordinary cell, it's straight to the northeast, and the left mover is going to peel off to the north-northeast fairly quickly. And you know what? If I don't like this photograph, oops, not that one, I can move the photograph around, to whatever you want. You notice it's got a little rubber band effect, so the adjacent points also move. That's just to save you time, so you don't have to move every point. You can move swaths. It makes it a little bit easier. I'll explain that line a little bit later. Okay, so how many say supercells? How many say ordinary cells? More super? Okay. Okay, let's go ahead. Oh, by the way, there's a function called Hale cape. You can highlight the -10 to -30 layer and see how the buoyancy is in that layer. But we need to do some more work, to provide better guidance as to what it means and all that. Usually I like to look for high buoyancies in this layer to get large hail, especially with high shear and so forth. Okay, well, there's a phase space diagram with all the ensemble members from the morning ensemble wharf that we produced. So they all paint generally the similar shear, but large variations in cape. And this is my storm type diagram that I use for distinguishing between supercell and ordinary cells. You notice I don't have multi-cells in there. And that's another soapbox of mine. The old diagrams where they put multi-cells in between super and ordinary. But we get multi-cells under lots of varieties of shear and cape. And so reality versus what we used to think based on numerical models of old are quite different. Another diagram I like to look at is this one. This is, and I'll show this to you on the BUFKIT. If we get an overview, we're certainly not using snow anymore. Let's go to convection. Okay, see this one says heights? I click that on and it automatically puts up just about everything, right? All sorts of different heights. Oops, let me go back to here. There we go. There it is. So we start out with the LCL right here, and the LCL is approaching 10,000 feet. And then we have the LFC, layer of free convection. So the higher the closer to the LCL is to the LFC, we often say, yeah, we're going to get convection in there, especially if the RH is high. Well, today, actually there is a period where the RH is forecast to be high in there. So the model is kind of bullish right here, and it's got this huge area of omega right in this region. So lo and behold, we might get something there. If we want elevated cape, we can click this on, and then I'm going to do something else to you. So you go to convection, and let's look at elevated sin. Now, why am I doing this? Let's take off omega. Look at this. Here's the elevated cape, contours of it. So every parcel launched below, within this region has a lot of elevated cape, whether it's launched from the surface or at near 8,000 feet, 10,000 feet. It's the same cape. It's probably because the LCL is so high. The moisture is mixed all the way through there. It's all the same. But notice the sin is red. Well, red is if I go back to convection, red says less than 20 joules per kilogram of sin for any parcel launched from this layer. If I launch a parcel right from the surface, I have to struggle through about 50 joules per kilogram of sin, and so it's blue. But because I'm phasing low sin and decent CAPE, these parcels that launch here can easily make it up to the LFC and make a thunderstorm. These are very important things to look at here to determine, what your likelihood is. I mean, you could just look at the precip plots and go, oh, precip bullseye, there it is. But precip schemes have their own issues and so forth. And so do explicit schemes out of storm scale models. So you can't take them all you have to kind of take them with a grain of salt. And this might help you to that end.
Hey, Jim, I was just informed that the snowmobilers are leaving at 12:30, so we might want to
Oh my.
go to a quarter of and
Yeah.
get some lunch.
Okay.
Okay?
Well, I don't know. What's that going to do with lake effect? Okay. All right, let's see what we got. So how many of you, what kind of weather do you expect out of this storm? How many of you, anybody bullish on tornadoes? All right, what else do you expect? All right, specifics. I want specifics. How much wind? How big hail?
Medium hail, lots of wind.
One softball.
Frozen hail. Debris ball.
Luckily, you'll be all frozen. Anybody going for, how about marginal severe winds? Hurricane force winds?
Sig severe.
Yeah,
Well, we did, for us convective people, we don't call them hurricane winds, we call them sig severe.
that's right. Sig severe is 65 knots, and golf ball size hail or larger.
Can you do all that together?
Why? Yeah, we could, definitely. I love hurricane hailers. They're the best kind of storm, as long as it's on open terrain somewhere else. Let's see. Okay, well, here's the storm off to the west. And these are some iPhone grabs off of looking at the radar image, and a whole bunch of chasers ringing the storm around here. There's the warning polygon. And this is our hail pad later on. That's Daphne's thumb. So we'll all have to measure her thumb to see and compare the sizes. But we had up to $half size. A couple stones are $half size. But I don't think any of those hit the pad itself. But people in town really got nailed. In fact, should I pull this up? Yeah, why not? This is a time lapse of the storm itself. Flag the downburst when you see it. So this is a supercell of sorts. It's not like the rip-roaring tornadic supercell, but it was a major hail-producing supercell too. A lot of people in town, which is right there, that's Norman getting pasted by winds up to 90 miles per hour with $half size hail frequent around there. And a lot of people lost windows, siding, shingles, and there was also high-end EF1 damage. We had roofs blown off. Not very good roofs, but roofs nonetheless. So that's a big Cape deep shear kind of thing. You know what? I'm going to go ahead and sail through this one because I want to compare that photograph with some others. So this is May 24th, high risk day. Look at the trough, looks actually kind of similar. It's just displaced a little bit south and a little bit stronger, but otherwise looks fairly similar to June 14th. Open wave coming in, except in this case here, our temperatures are a lot cooler. We got a less of a cap, so it doesn't have to get as warm, and the dew points are higher. So there's the setup. Storm's firing on the dry line. This is the case that Paul showed the other day. Now look at how much red you got. You got red everywhere except for wet bulb zero height. LCL is yellow, though I'd call that red for that day. It was optimal, I thought. 80/70 with a 10-degree spread yielded almost perfect LCL height. And look at that hail cape right here. I turn on hail cape. Look at that buoyancy in there. Those updrafts probably have a temperature surplus of 15 to 20 degrees at times. So here's the cape's shear phase space, and you can see it's nearly at the top of the charts because of the cape. It's not excessive shear. I mean, it's good shear. You know, don't get me wrong. It's plenty for a high risk. But it's not the kind of shear that we saw on April 27th. That was a lot stronger. But I think when you get to a certain point in time, it's enough. The hodograph was kind of weird this day. This is not a giant looping hodograph that you see. But there was more than sufficient low-level shear in this so that you could get plenty of action out of that. So there's a curious thing that goes on here. You notice this white line. Boy, am I opening a can of worms this late in the day. See that white line right there? This is a tool in BUFKIT. And I'm going to have to go to I have to pull it out. I'm sorry. Let's go back. Let's get the sounding data. This is too good to ignore. Hopefully this will do it. Okay. Copy and replace. Hopefully that did it. If it doesn't, I'll just use this one. Oh, that was June 14th still. Let me see. Good God. I'm missing it all over the place. Well, I'm going to do it this way. Okay. One of these days, if I understand Windows 7, I might actually get there.
This will go away when you put it to Mac.
Yay! Well, you know what? I'm gonna do this no matter what. I'm gonna just go ahead and use the current case here. This will take too long otherwise. So we got hodograph here. Right mouse click pulls up a boundary. Why am I doing this? Well, say if you have a boundary with a bunch of storms lined up along it, and you want to know, are there going to be collisions between these storms? This is a key thing. Some ways you can find out ahead of time what's going to happen. What often happens is you have collisions between, when you have these high shear events, you may have collisions between left movers and right movers along the line. And you can actually make some assessment as to whether that's going to happen. Or you can look at the observations of the storms interacting and then adjust the hodograph to some kind of reasonable fit. So in a frontal relative or boundary relative space, now all motion is relative to the boundary. So this, you see on the hodograph here, this mean layer here, the steering, it's on the boundary. If I pick the boundary motion to the east at, let's say in this case here, 8 or 9 meters per second, the mean storm motion will be on here for the mean flow. The right mover would actually fall behind the boundary. You see this here? The R is off to the left. The L is actually fairly close to the boundary. Well, how about this? If I had a boundary moving to the southeast, now all the storm motions are going to fall behind the boundary, and they'll quickly experience whatever air mass is back there. If it's a hostile air mass, it's quite likely then the storms will either line out or cold pools merge or dissipate. So if if I'm a masochist and I want isolated storms, I may want to have the boundary in such a way that something like this. Here's a stationary boundary. Right movers pulling ahead of the boundary. Left movers peeling off but way ahead of the boundary and quite likely will miss whatever right mover's up here. So let me visualize that for you some further. Here we go. This is the boundary on May 24th. It's moving to the east, roughly about 5 meters per second. Right mover is actually going to pull out ahead. Left mover is supposed to pull behind it and miss whatever storm is up here. Let's see what happens. Some of these storms, you can see the first one here, Canton Lake. And then we have other storms that are trying to turn into supercells. Here's the big one, El Reno. See these storms merging into it? Uh-oh. There's a bunch of storms merging into it. And look down here. Watch down here. You see this left mover? And then here's these supercells coming for Norman. Here comes the left mover coming in. Slam. Oops. Storms close together. Left movers hitting right movers. Ordinary cells hitting right movers. All the tornadoes dissipated off to the east. Let's see if I get this. Come on. There we go. This is what was supposed to happen. Want to see that again? That's what was supposed to happen. But instead, that didn't happen. So I came up with I kind of modified the photograph by dragging the rubber band so that the storms lined up equidistant ahead of this boundary, pacing the boundary. So that if there was a storm up here, right mover coming in, it could potentially get hit by left movers and ordinary cells and all that kind of stuff.
Are you saying the model wasn't very good?
Yep. I'm actually trying to fit the observations of the model, and I don't know if I should be doing that, but I think so. I think what in this case here is that we're looking at using the observations to try to help you explain what the storm behavior is doing. And so it's kind of a reverse of what it is before, and it really works well with the RUC because the RUC is a rapid update cycle, and it can do that. But you can do that with the morning model or the 18Z run or anything like that.
Does it seem like there's a sea breeze application with that?
You betcha. You know, in fact, it's Jim Wilson and Pam Meganhart that did a study down in Florida some years ago, and they found that the biggest influence of convective coverage on sea breezes was whether or not the mean steering layer flow of the initial cells was going to ride the boundary or not. And if it rode the boundary, expect big coverage. So if you had, let's say, a southwest flow environment, you would expect, let's say, the sea breeze coming in from the west coast to be riding along with that steering layer flow and produce a lot of storms.
Like
Now,
West flow usually does it for us, 'cause in the
right,
sea breeze and properties.
right. Now there's a gotcha with that. The east coast sea breeze is going to experience high convergence. So you may get storms firing up very quickly there, but they may not survive very long. They may quickly go offshore, and then that's it. Whereas the other ones will just keep going. So in this case here, I put the same boundary motion on here, and you can see the storm motions are a little bit more parallel. I couldn't quite, you could angle it in different ways, depending if here's the EWRF and here's the RUC, and so forth. So just had to tweak that photograph a little bit more to match reality. So the tornadoes dissipated, all except this one. This one kind of just dissipated on its own, even though it got slammed by one storm after another. But these were too close to each other, so I think this storm interfered with this one. And then this storm, the left mover hit it, and it dissipated just southwest of the weather center and left a shower of debris that Paul showed on the dual pole the other day. So I think I'm running out of time if I'm, let's see, I got 7 minutes more. Let's see, should I go through the pain and show April 27th? Sure. Uh-oh, I knew you'd ask for that. Dope. This is Windows 7, right? Let's see if I can, okay, let's try to load up desktop. There's Breckenridge, BUFKIT cases. Let's see, which one do you want to pick? I have several folders here. Let's look at Ensemble WRF from that morning. That'll explain that to me. All right, we'll look at the 18Z RUC. And I'm just going to pick Which sounding, you want to look at Huntsville or Tuscaloosa? Okay. Geez, where'd the photograph go? Okay, we have to zoom out. And there it is. 0 to 1 kilometer shear. You want to look at 0 to 1 kilometer shear? Watch what I do here. I'll click on the 1 on the right. And there it is. You get a good view of the 0 to 1 kilometer shear. I like to see 10 knots for upping my chances for significant supercell tornadoes. In this case, each ring, again, in the photograph is 10 meters per second. That's 20 knots. So there's 20 knots right through there. We're not even up to halfway on the 1 kilometer layer. So it's really 45 knots to 50 knots of 0 to 1 kilometer shear. Look at the Cape shear space. There it is. Starts out low, extremely high shear, higher than May 24th. Not as much Cape as May 24th. But firmly well within the supercell phase space. 0 to 1 kilometer shear. I just click on that. And 40 to 45 knots in that layer. He's in Cape. So well in excess. I would look anywhere to the right of like 10 knots over here. So extremely high values. And again, this is Huntsville. Huntsville started out north of that outflow boundary, and they started out in the 50s. And within 2 hours, they modified to the 70s, just in time for the storms to hit. So let's see what the indices look like. Okay, lots of reds, and wet bulb 0 is a little bit high. LCL is red in this case, you notice that? Right there, it's extremely low LCL, less than 2,000 feet. And so forth, so it's pretty dramatic, Okay, I think we can show something from, let's go NAM here. Click on that. Any questions, at least in terms of photographs and everything else? I mean, I've covered probably about 60% of what I was able to cover, at least up to this point. It could be about anything. If I don't get any questions, I might be forced to show a lake effect event. If I can find it, that is.
I can pull you aside later.
Oh, okay. Because I do have Ensemble Wharf signature right here. Although that only goes out to 48 hours, and I think that might not be enough. Oops. Or I might not be able to show the overview. It's getting cranky here for some reason. Meanwhile, if you guys got any questions about anything that I showed, otherwise you appear to be all stunned.
Drink it from the hose.
Like I say, I could do another session on the just on the convective part of this whole exercise. Okay. Yeah.
Jim, what's the future of BUFKIT? We saw there's a new version just came out.
Yeah.
Are there other new versions scheduled? Do NWS budget cuts have any threat on the future of BUFKIT?
Only on the thread of Ed's ability to program new features into it. Future of BUFKIT, good question about what the future of BUFKIT is. 4 kilometer wharf soundings are going to come out. Also going to work with Ed to update the indices part and modernize and align them with SPC indices so that you can go from the SPC mesoplots straight to this and have a direct comparison. But the one thing we want to do is for things like the SIGTOR parameter or the other composite parameters that involve multiple inputs is to pull out those inputs and show them to you. Show the value of the contributing factors and then the final solution. And so we have to figure out how to visualize that, but it might be a significant expansion on the indices panel that you see there.
How often do you all try to update it? Do you have a set time frame?
Well, it's it's a labor of love. This is not part of anybody's official work, if you can imagine. So it's kind of as time permits, so to speak. So
What if Ed gets hit by a truck on the way to work tomorrow?
what if Ed gets hit by a truck? Well, you know what? The source code is freely available. And that's the thing, or else I'm going to have to start learning source code too. Actually, Pat Marsh, who's a graduate student at OU, is very interested in creating a Python-coded version. But it takes a long time to get to something as mature as this, and this is 20 years of work, basically. So it'd be nice if we could get the Weather Service to officially adopt this, or some private agency. I mean, it doesn't have to be the Weather Service to adopt something like this. Anybody can take this and run with it and really make it into an ecosystem and a business model, really. I can imagine. Okay, I think, are we due to stop here at about quarter of?
Yeah, it's probably about right.
Yeah. Okay, if you got any questions or you want me to show anything, once I get off of this strange Windows 2007 computer and go back to my old Windows XP, I'll be able to zoom through profiles a lot faster. So.